In this next group of problems, we're going to do something very similar, actually a little more simple than what we did in the previous set of problems. And that is, we're going to define what is called the average value of a function over a given interval. And it goes like this. So we have a function from a to b, and we know that there is an area under the curve between the curve and the x-axis from a to b, and that is given by integral from a to b f of x dx, assuming that this curve is the curve of f of x. And we've seen in the previous examples that there is some height that forms a rectangle with the same base as the area between the curve and the x-axis, and that is f of c times b minus a, where c is an x value. There could be more than one, where the height of the function at that point defines a rectangle whose area is the same as the area under the curve between the curve and the x-axis over the same interval. Well, we're just going to take a small, make a small change or a small adjustment on this formula and isolate f of c, and we do that by multiplying both sides by 1 over b minus a. And this new quantity here, that f of c, we're going to call the average value of f of x on the interval from a to b. So whether we call that f of c, we call it 1 over b minus a times the integral from a to b of f of x dx. That height of the function there, we're going to call that the average value of the function on that interval. Now, the average value of the function, we could take any number of points and add up those points, divide by how many points we have, and if we took enough points evenly spread out, we would get a fairly good estimate of what the average value of the function is on that particular interval. And remember, all we're doing is adding them up and dividing by the number that we have, right? Well, in a sense, that's what we're really doing with the integral, is we're adding up all of these y values and dividing by the width of the interval. So it's very similar to the process used for finding an average of a group of numbers. Anyway, the way I call this is the integral over the interval. And what we mean is the integral divided by the width of the interval. So you're going to find the integral, divide it by the width, that means b minus a. And let's see what that looks like. Actually, we've been doing this all along with the previous three problems, but in the previous three problems we went even further, and we identified the x value c where that happens. So let's get going here with number 51. We have the integral from -3 to +3. And again, we want to divide that by the width of the interval is 3 minus -3. And I'm going to rewrite that. So 1 over the quantity 3 minus -3, which is going to turn out to be 6, times the integral from -3 to +3, 9 minus x squared dx. And we'll see it's not really that anything much different. We're just taking the integral and dividing it by the width of the interval to get what we call the average value of the function that's graphed there. So antiderivative of 9 is 9x. Antiderivative of x to the third of x squared is x to the third over 3, from negative 3 to positive 3. And this comes out to be 1/6 times. All right, so we have 9 times 3 is 27, minus 3 to the third is 27 over 3, which is 9. So that's the antiderivative evaluated at 3, minus the antiderivative evaluated at negative 3 is negative 27. And then we're going to have minus negative 9. All right. And finally, we have 1/6 of 27 minus 9 is 18. And negative 27 plus 9 would be minus negative 18. So that's 1/6 of 36, which would be 6. Now on the calculator, I'm going to show a little bit different way of doing this than we've been doing in the past. It's another strategy that's also very helpful. All right, so we're going to start off by putting our function into y1, and that is 9 minus x squared. And then we want 1/6. So 1 divided by 6 times, and we're going to go to the math key here. At the bottom of the math key, you have this option 9. It's the function, it's the integral function. So the integral function, and you need to put in the function that you're working with. So we could put in 9 minus x squared. 9 minus x squared, and I'll show you another way to do that when the function is a little bit more complicated. 9 minus x squared, and then a comma. That's over the 7 button. Then you have to put in the variable of integration, which is x, and then your lower limit and your upper limit. So what we want is 1/6 times the integral of 9 minus x squared dx from negative 3 to positive 3, and we end up with 6. So this is also a good way to do this because you don't have to set up a viewing window and wait for it to graph the window, and you don't have to wait for it to shade the area underneath. Alright, I'm just going to show you one more thing that we can do with this. If we hit second and enter, we can call up the last function. So instead of putting in 9 minus x squared, what I'm going to do is I'm going to call up the function y1. So we go to variables here, and then over to y variables, and then function and y1. So it's a few things to remember, and I don't want that x squared in there anymore. So instead of putting in the function 9 minus x squared again, I already put it into y1, and this gives me a way to reference that function there, and you can see that it gives me the same exact value here. Alright, we're going to go on to the next ones. So with 53, we're going to start with the integral from 0 to 1, and integral from 0 to 1 of x cubed dx. We're just going to divide that by the width of the interval, which happens to be 1, so that's really not going to affect anything. And so we have x to the 4th over 4 is our antiderivative from 0 to 1, and that's just going to be 1/4 minus 0, which is 1/4. And we'll practice using the calculator again. So second enter brings up the last statement, and so in this case I don't have to put this 1 over 1, but I can, and my limits of integration are going to be from 0 to 1, delete the rest of it. And I do need to put in our function into y1 equals here. So that's x to the third power, x to the third power, oops, x to the third power. We need to delete that last character. And now we're ready to go. And so it tells me that that's 0.25, which is exactly what we had. Alright, let's try to get the final one here. Sine of x, number 55. I can squeeze it into this area down here. We have the integral of sine of x dx, and that's from 0 to pi. And the width of the interval is 1 over pi minus 0, which is 1 over pi. Alright, so the antiderivative of sine is negative cosine, 0 to pi, and so we have 1 over pi times, and actually I can bring out the negative since that's a constant multiple. It'll make the calculations a little bit easier. So I have cosine of pi minus cosine of 0, so negative 1 over pi times cosine of pi is negative 1 minus cosine of 1 of 0 is 1. So we're going to end up with 2 positive here over pi. Alright, so 2 over pi. Well, bring in the calculator. Alright, so let's put in our function real quick here. And we have sine. So sine of x, and no extra characters there. And alright, so I want this to be the width of the interval is 1 over pi. So I have 1 over pi, the integral of y1 x from 0, which we have, up to pi. And so all I have to do is change the pi there and run. And it says that the answer is 0.63 to 0.6366. So let's see if that equals 2 divided by pi. And it's exactly the same. So there's a way of finding what we call the average value of the function. It's the integral divided by the width of the integral divided by the width of the interval. Alright, we'll go on to the next set of problems in the next video.